your department, which is something, the way you run it, and many other, in many dimensions, is how we aspire to run. Anyway, so I'm very, very happy to be here. So today I decided to have this cryptic title. Now I have to reduce my volume. Good. So, which is 2 tales about time in living and not so living transport networks. Now this is cryptic, as I say, but it will make sense. Now, we'll be very low level, let's say, and please interrupt me with questions. I didn't add too much. And hopefully we're going to have discussion in the end. So, when you hear the word transport networks, which is what I will be talking to you about, you probably think about airplanes, trains, and automobiles, and maybe this movie, the movie buffs you might have encountered. So we have links connecting nodes. The nodes could be airport hubs, it could be railway stations, it could be road intersections. We have those links being aeroplane routes, train tracks, or roads. We have load, which could be people, cars, or products that are transported on the link. The nodes can be weighted. You have big streets and small streets. And also, this is important, there are constitutive laws that connect the load on its link with properties of that link. Now, these were transport networks, but these are also transport networks, like the network that distributes water to our houses, power grids, rivers, our own circulatory system, plants, which is probably what you heard in the talk 7 years ago, although I don't remember, respiratory system, and this is Physarum polycephalum, which is the darling model organism for physicists that want to study this type of networks, because it's very, very easy to culture. Well, easy. It's easier than other things. And it has been shown to adapt. So these are pipes, let's say. These are channels that remodel, constantly remodel, depending on where the food is. And it has even this organism, which is essentially a unicellular multinucleate organism, has been solved to be able to solve even mazes using basically self-organization principles. Now, all of these, if you linearize them, and I've had some interesting discussions with you today about these problems, or if you simplify them, they become a network problem, which we can tie to simple resistor networks, physics 101, or fluidic networks. And the current for most of what I will show is what will be called I, the current through the links. Then I have the net current at a particular node. And if the node is, the node can be a net source or a net sink, depending if the current is going in or is going out. I have the weight of the edge, which could be the conductance. And then I have the pressure, which is a field defined at the nodes. And this is what pushes the fluid around. And this relationship is current conservation, and this relationship here is the constitutive relationship that I was talking about. It basically tells us how the pressure drop connects to the conductance. And if this is linear, this is Ohm's law. Okay, now this is another transport network which doesn't look like a transport network at all. This is random walks on a graph. Now, this is my second part of my talk, and you'll tell me this has nothing to do with the networks that I showed you, but you can show mathematically, depending on exactly the question you formulate, this random walk on a graph, or the drunk person losing the keys and looking for them on this network, that maps either identically or very closely to the math and physics of these networks, which is really, really cool. Now, going back to some very, very basic questions, and again, this is very simple and very introductory, but this is still a warm-up, let's say. Let's say I want to ask questions related to design and optimization of transport networks. Let's say I want to minimize dissipation, which is the energy lost to to viscosity, basically. And I have this network here, and I have my source here, and my sink here. Now, I could ask this audience what would be the optimal topology for this, but I won't, because what you will tell me immediately is a direct path, right? That's the most economical way to connect source and sinks. And in fact, one can do the math, and they can show that. Now, it gets a little bit more interesting if you have one source and many sinks. You could connect directly. Or if it pays to combine, if there is what we call economy of scale, if you get more bang out of your buck by making bigger pipes, you can perhaps combine this up to a certain level and then distribute from there the links, right, the load. Now, what's important here, both here and here and here, is that this network is geometrically embedded. The distances matter on how I put my channels, my pipes in. And now another thing that I showed you in all of these networks, these were tree-like networks. They didn't have any cycles. But in a lot of these networks that you see in this background, including river networks, you have loops. You have cycles. You have more than one way to go from one node to the other. You can go from here to here using this path and using this path, for example. And a big question in my group is what makes these stable? What stabilizes loops? Why? Because it has been shown mathematically, and this is a result that is in math books for transport networks, and it can be shown with not great difficulty, is that if you have a dissipation minimizing network, it's going to be a tree. If the cost to build the network scales like this is the conductance, which is a proxy of the cost, how much you're paying to build the pipe, and this gamma is an exponent. And if this exponent is below 1, the network is going to be a tree. And if any physiological network that I will be showing you, this gamma is smaller than 1. That means it pays to combine. Like you pay for big pipes, you pay progressively less cost. And one easy way to do it is to put gamma equals 0, where you see it doesn't matter how big, how much conductance you put in, you pay the same amount of money. So yeah, you might as well prioritize big pipes. Then we have the dissipation, or you can look at other cost functions, and then you can find that things are trees for physiologically interesting gammas. Now, you optimize, if you add bells and whistles, including asking to requiring robustness, requiring the network to remain percolated if you cut a single link, then you start getting loops. And these simple optimization models will reproduce quite nicely, qualitatively, features that you see in nature, like in leaves, for example, these connections between the secondary veins and other features. But I'm showing you all that because I want to point to you to something else which is very, very important, and that is asking optimization questions is useless in biology by itself because you have to make it somehow. And perhaps the available developmental pathways that you have or the constraints won't let you go there. This here is a movie from this paper of the developing chorioallantoic membrane of a chicken egg. The chorioallantoic membrane is essentially the chicken placenta. You see a top view here. And what I want you to notice is in the beginning of this loop, right here, for example, you see capillary plexus, just undifferentiated, very loopy and hierarchically flat venation. And then you have this hierarchy emerging, right? So there's something interesting is happening here. Now, that interesting thing that's happening has been in our mind for some years now, to different degrees. And it is an equation that people have been kind of using, accepting in different systems. For example, if one looks at some models in the literature for shear stress vascular adaptation in animals and translates those equations, those fields, to flows and conductances, they would get this equation. This equation tells you that the conductivity or the conductance of a pipe, the rate of its change, will increase if there is lots of flow through it, and if there is little flow, it will disappear, right? And that equation here was actually proposed ad hoc for Physarum in a very now famous paper. And in fact, if you look at the fields for the auxin canalization model in leaves, and you, instead of conductivity, you call this something else, pin polarization, and you call this something else, auxin flow, and so on and so forth, you get to this equation with an extra field here, which is like spontaneous production. Now, this means at the stable steady state, if you set the current equal to 0, your steady state now is having some vessels. This is a capillary plexus. This is an interesting equation because it only relies on local information. This is very satisfying as a physicist if you want to do self-organization, because each vessel only knows the current or the shear stress through it and its conductance, its radius. So it's actually very nice because you can get development to happen without somebody orchestrating it, without an architect. Now, really quickly, how we do what's under the hood for a lot of for some of the results that you're going to see. We start with some underlying potential topology. Let's say we put some boundary conditions, sources and sinks. In this case, source, sink. We sprinkle some initial conductances. We calculate the currents, and it's a fun solution to do. In this particular case, we have growth. We assume that the whole system is growing. We plug the new currents in here. We modify the conductances. We take the conductances, we plug them in here. We find the new currents, and so on and so forth. Until we progress, we move into time, and we go to some equilibrium. And in this particular case, you see how this very simple local information equation recapitulates what's happening from the capillary plexus to a fully organized, differentiated vascular system, like what I showed you in the complicated movie. OK. So any questions here? No. So this is the first tale, because now I'm going to tell you that this is not as simple as it looks like after this kind of fast introduction. I'm going to start with my first tale, and that is I showed you these equations, and there was no beating heart. I assumed something about the in and the out. The pipes were rigid, and there's that. The problem is there is in many organisms there is periodic forcings, which is something that we have been more and more excited about. So this is a picture of a heart beating, and I want you to look at the heart, and I also want you to look at this vessel here. With every pulse, it changes diameter. This is because our vessels are elastic. This is called the Windkessel effect, basically. Now, this heart pumping creates a pressure pulse that is propagating in the arterial system. And this is why you can feel your pulse here. Now, this made us worry about other systems, and that is a general. I've talked to you about this a little bit, and I promise that I'll also show a nice video, because this is really cool. This problem is we share with many organisms, including this jellyfish that you see swimming here, this periodic motion that has to somehow propel the fluid in the gastrovascular canals that you see here. Right? So I'm not going to talk to you about this, but it's really cool that problem of propelling flow, everybody has it. And it's intimately tied, as I hope to convince you, to the structure of the circulation. Now, going back to, let's say, the heart, or even not the heart, a very simple resistor network. Let's say you need to push through your capillaries a current this much, like this red line, right? The heart, though, is giving you not a DC current, it's giving you an AC current. Now, if I look at the power dissipated, if I give this current not as a DC, but as an AC current with the same average, I pay a cost in dissipation. And dissipation is the energy that the heart needs to give to the system. So I would like to think that somewhere, somehow, the body would like to very quickly near the heart attenuate that signal. Maybe make a gigantic capacitor, something very elastic that kills the pulsatile energy and converts AC to DC to save on that extra power loss. In fact, the elasticity of our vessels kind of do that. This is roughly pressure here, and this is roughly, heart, and then you go to aorta, large artery. As you go from near the heart distally to the capillaries, the pulsatility decreases but remains even in the capillaries. Our body expects pulsatility, right? So we think, or we would like to think, that the body maybe it's useful for something, and that's a separate paper, but at least our body knows about it. And we know it knows about it because there are people that don't have pulsatile hearts, which tell me this is crazy. And this is actually why I got into this problem. This question was brought to me by an MD, PhD, not working on this, who told me, there are people walking around that have these LVADs, which are continuous flow hearts. So these people, maybe they get sick and they go to the emergency room and they forget, maybe they, break their leg and they go to the emergency room and they forget to tell the nurse that they have an LVAD, and the nurse, the first thing they do is take the pulse, and the nurse freaks out because they have a person talking to them that does not have a pulse. These are bridge to transplant devices, because if you have a heart failure, end-stage heart failure, you die if there is no donor. This can keep you alive for several years, and the several years keeps getting longer and longer now, the better this becomes. Dick Cheney had one. The problem is that for engineering purposes, these were continuous flow. Now, they start developing pulsatile flow artificial hearts, and the reason is they've been noticing in patients that were actually to begin with quite sick, but they're noticing that this continuous flow heart creates other problems. And a lot of them are vascular remodeling problems, means that their vessels in their body, in the stomach, everywhere, they see a continuous signal, the absence of this pulsatility, and they start changing. Remember this equation? I'm going back because I didn't arrange my slides properly. These equations, they read this equation with different currents. At least this is what we think. So we started worrying about this problem, and us being physicists, we did the simplest possible problem, where we took an elastic pipe, we took the Navier stocks and we one-dimensionalized them, we turned them into all this complex 3D flow. We made some assumptions, kind of too aggressive a little bit. And we have now one equation for the flow. It turns out if you do that, you get some very nice simple system that makes circulation looks like the flow through a pipe, look like a transmission line, which is really cool, a simple transmission line, because you can get length scales and you can get time scales and you can understand what's going on. And it all boils down to a mass conservation equation. This V now is pressure because it's voltage, right? And force balance, right? The pressure drop, this is acceleration basically, and this is viscous, the viscous term. So you can get these quantities that connect directly to biological quantities that have to do with the elasticity of the vessel. This here tells you how compliant the capacitor, how compliant the vessel is, because essentially you store fluid, it expands, right? This inductor here is inertia, essentially, because to accelerate the blood you need energy, and this is viscous resistance. So with this very simple model, the first thing you can do is that you can look at the pulse amplitude, how it drops. And this lambda is a very important quantity that tells you, you have the pulse here, should you feel it here? Should you see it at the capillaries? So again, very simple model. Now, we took this very simple model and we made things worse by saying, okay, we're physicists, we're going to do the spherical cow. We have to understand. I'm not going to go and try to understand the whole human. I want to understand the spherical cow. And the spherical cow is a one-loop system. This is the heart, and this is one loop. I have R1 and R2 are the radii of my two vessels. Now, my apologies. This gamma here is related to the other gamma that I showed you. It's not exactly the same gamma. There is a linear function. There's a function that connects them. But the thing to know here is, I have it somewhere here where it's what's for humans and what's for animals. Now, the critical gamma is 1/2. Now, what happens for critical gamma, this is the flow diagram. I start anywhere here. If I start at this green dot in this flow diagram, which is these quantities here are 1, 0.5, and R2, 1.5, I'm going to flow to the edge, to the boundaries, which means only one vessel is going to survive. In this case, R2. So there is this, the fixed points, the stable fixed points are at the boundaries. Loops are unstable. I told you about this earlier, right? There is no pulsatility yet here. And the pipes are, yeah, there is no pulsatility. This heart is, yeah. Now this, we know about this in the human body. It's called vascular shunting. You lose vessels. You lose, if you have parallel paths, you're supposed to lose them. Now in reality, this happens mostly when something goes wrong, like in cancer, for example. The people, physiologists have been worrying about this, and they're thinking about mechanisms where several paths, redundant paths can be stabilized. Now, what we do here is we added vessel compliance and fluid inertia. So here, actually, what I didn't tell you is that the vessel here, it's not just omega. These were rigid vessels, right, which is a bit stronger than the omega that side. Okay, so for gamma larger than 0.5, which is now critical gamma, what happens is that for some frequencies, pulsatility, if I add a pulsatile heart here, stabilizes loops. What does this mean? This is omega equals 0. This is omega equals 1.8 pi. And if I start anywhere here, not too close to the boundaries, I would go to a fixed point with a loop. And this here, the lengths of the vessels are of the order of this lambda, which I told you it's how fast the pulse dies. Because if the vessel is too long and the pulse dies too fast, it doesn't matter. It's like you have no pulse, right? You killed the Windkessel. Okay. Now I'm going to quantify it a little bit better for my simple model. How to read this graph? Blue color means no loops. Yellow color means loops. This order parameter here gives you a proxy of how big of what part of this diagram, of this flow diagram, what fraction of initial conditions are going to take you to a stable fixed point with loop stable. So you see yellow means you have a lot of it. Almost certainly you're going to stabilize your loops. This axis is gamma. For gamma smaller than 1/2, this is the result I showed you earlier. It's unphysiological. Biology is not there. There is no biology there. And everything is a loop. We don't care about it. This red dotted line is gamma it's basically a little bit above it, 0. I think 5, 6, something like that. So let's start here at 0 frequency, blue, no loops. As soon as I enter this frequency here, I've stabilized loops. I have something that I wouldn't have without pulsatility. And this result persists for longer pipes, but you see now it's more difficult. There's less, things change a little bit. It's more difficult to, it's true for lower gammas, closer to the transition point. Yes?
Why are loops good? Why is vascular
yes.
bad?
Excellent. Two reasons. You're asking why do we need them in our body? It depends. It depends on the primary role or so the vascular. Now I'm going to put on my physiologist hat, which I don't own, so there's a problem. We have two types of vessels: one to go long distance, and one to do the gas exchange, the nutrient and oxygen, whatever exchange. So for the pipes, the highways, let's say, loops are somewhat useful because if you get an occlusion, you have a multiple path and you're not going to die. This is critical for the architecture of the brain, where at the surface you have the surface arterial circulation, which is very, very loopy, which is not what feeds this is not where the exchange happen. This is what it distributes the blood. So you get micro-occlusions to that all the time, but there are multiple paths. In mice that are otherwise indistinguishable, in strains of mice that are otherwise indistinguishable from mice that don't have this mutation, mice that with less loops, they're very, very sensitive to stuff like vascular dementia, where you get a lot of microstrokes and you lose more and more and more functionality of your brain. Now, for the smaller stuff, for the capillaries, it doesn't matter. You get occlusions all the time. Well, at COVID, people got too many occlusions, and now they think long COVID is related to too many occlusions in the microvasculature. The microvasculature is full of multiple paths. Probably the reason there is because there are fluctuations in where the blood needs to go. The reason there is not as obvious as redundancy, but it is better because you have fluctuations in directionality, let's say. Okay, now if the vessels had an equal length, again, the result persists to be fast. And actually, if you start adding loops to go a little bit, to make that spherical cow a little bit more ornate, you add ears, for example. Now, that my parameter with the phase diagram, we cannot do it anymore because my z parameter, okay. I'm having, shut down. No, I don't. Cancel. There we go. So here, remember the z. That I cannot do it anymore, so I need entropy. This is basically a proxy of how many parallel paths I have, and the story persists. Gamma smaller than 1/2, a gigantic loop, everything. 2/3, which is more or less in this, for this gamma, what humans are. You see the story, stabilized loops. And again, for more loops. And I'm going to dig in a little bit further to this esoteric diagram. Here you see frequency, and here you see fraction of what actually the states look like that are stabilized, because now I have, in this case, I have 1, 2, 3, 4, 5 vessels. I have lots of vessels to worry about. The parameter space dimensionally, explodes. So when I don't have loops, these bluish colors here, if you can see them, is these. Here that I have loops, primarily is this state where all the loops get stabilized. And this persists even for more loops. It's this red one is the one that's overrepresented. So it looks like when you stabilize everyone, not just the small ones. This is very preliminary. Now, we submitted that for publication, and one of the referees complained very, very vehemently that our model is too simple. And we came back saying we like simple because we're physicists and we can get all those lambdas and those taus. No, you want the full model. So we redid everything with the full model. And the good thing is with I'm not showing you the full model. It's horrendous. The good thing is that for when you add dimensions to this, when you put numbers, our pulsatility is basically around 2 in these diagrams. We lose the resonances, which we know why we have resonances. We lose the resonances, but for the part that we care about, it's a this yellow part, we keep having it. It's very, very robust. It's a very robust effect. So it didn't go away with a very different model, because the physics of what we cared about, basically a transmitted pulse, was captured by the simple model. And now I'm going to go from this scale, which is microns, to kilometers, not because I've lost my mind, which that has happened, as the people that saw me looking for my phone can testify right before the talk, but because we've realized that rivers are like our own circulation, as Da Vinci had said. Why? Because rivers, like our own circulation, does not just happen out of the blue, it adapts. An example is the wax delta, which formed due to a mistake, essentially. They dredged the wax lake, and then in the span of less than 50 years, you got a new delta. It's still evolving 80 years later. This is here. Now, another thing interesting with deltas is that, much like our body, there are deltas with less loops, tree-like deltas, and deltas with lots of loops. So we thought, and this was an undergrad, by the way, an undergrad project, which was really, really cool that an undergrad did all this, to study this. So what's important here? So this is a network, right? And we have the water coming from the mountain, and then this is the sea. And we add to simulate tides. These are tidal deltas, right? To simulate the tides that are always there to some degree, I have to say. It's not that they're tides and they're not tides. It's a continuum. To simulate those tides, because it's an undergrad project, we had to make it simple. We did something artificial. We put in internal nodes that act as internal sources and sinks that would swell the amount of water in the river, or they would decrease it. And we defined a dimensionless quantity, the relative tidal flux T, which basically how much water is coming from the mountain. I'm sorry, the opposite. How much tidal volume comes in versus how much water comes in from the mountain. This competition of two forcings, let's say. So in the undergrad did the simulations. Adam Konkol. And here, for visualization, I marked the loops, and this number is this dimensionless number. And here I'm counting the loops, basically. No tides. No loops. Too many tides. No loops. Intermediate tides, lots of loops. And then we went to 28, if I remember correctly, deltas around the world, wherever we could get data. Everywhere. We did not do any data cleaning. This is about 13, because I put them on a Google map, and I got after 13, I said, this is too much for me, and I stopped. So you see everywhere in the world, we did not do any. If we could get the data, we used it. And the green dots are the deltas, which could be Arctic deltas, anything, any type of rock, any conditions. Dimensionless tides versus essentially loopiness. This is theory, and this is reality. And we can, of course, we have some outliers, but we can recapitulate this. We are consistently off, and we know why, because we cheated. We did these internal nodes, and we have done things to move towards the correct direction, and that fixes. This moves the theoretical curve up, but this works because tides are like our heart. Okay, So this brings me to the last part of my talk, and it will look like a U-turn, but you'll see the same patterns, and that is time. And I'm going to tell you about networks. I'm going to tell you about flows in networks. And now time, and you'll see how time also can affect, the considerations of time can also affect loopiness, right? So here I will tell you how minimizing search time can mean less connections. And now we're going to go to this paradigm. This is a random walker that is drunk, the usual trope, let's say. But now they live in a city. This is a grid. This is, they lost their keys and they're walking in the streets of the city around at random, diffusing. And because they're physicists, they're thinking, would I be able to find them better if actually there were a lot of bridges and I could teleport from intersection to intersection like this? Or is this a better way? Again, you see the question of loops. And let's mathematize it a little bit more. I'm going to be talking a lot about mean first passage time problems, which is the average time for a diffusing particle to hit a target for the first time. This is the home, and I'm doing random walks, and then I'm counting on average how many steps or how fast I will reach here. Now, I can go and I look at all pairs of nodes, sources and sinks. I want to design a city where people will be able to find their stuff, like me, my phone, in the minimum amount of time, regardless of where they lost their phones and where they're starting from, right? So what type of structure is optimal for an all-to-all search? And as you'll see, this is going to start becoming, the language is going to start becoming a lot out of a flow diagram. So this is a network junction. This is the random walker. The edges are weighted. And depending on the weight of its edge, the walker will decide which link to take. The walker will preferentially take links with bigger weight. But also the walker spends time crossing those edges. And this is a very important quantity. The walker diffuses on the edge. The walker is drunk, so the walker cannot decides at random which direction to go. But also, as soon as the walker commits to that edge, the time it will take to go the other way scales like this. There is the length. Remember, my networks are geometrically embedded. There are distances. And this t time scales as the length to 2 beta. And in this, again, weird notation, beta larger than 1 is subdiffusion, and smaller than 1 is superdiffusion. And beta equals 0 is just regular, only topology. I kicked geometry off the equation. And beta equals 1 is diffusion. OK. So we got actually inspired to do this problem from Kostlover's work from UCSD, walking on the endoplasmic reticulum, and then we realized this is not at all. This is what we're doing is theory fantasy. Then we actually, honest to goodness, realized this can be with language that I will not share in this talk. This can work for energy landscape, for studying energy landscapes. But the funniest of it all is that I got a grant with a string theory. I don't know any string theory whatsoever to use this for high energy for the multiverse. And again, I do not know anything at all. But it turns out there's similar considerations. OK, so back to this random walker, which in this seminal Michael Fischel paper has to be an Englishman, a lone drunken Englishman. This is a wonderful paper, by the way. So now it's a ring. The city is a ring. And the Englishman, the drunken person, the random walker, starts here and is doing the process we said for these graphs. Now, the question I'm going to ask is, do shortcuts improve the search? If I add a street from here to here, will it improve the search, and under which conditions? OK, this is graph number 1 and graph number 2. This is total search time. Remember, it's all to all. This is my original city with forgetful people losing their phones. And this is an improvement I'm suggesting. And this is graph type. Well, things are not as you would expect. This deteriorated the total search time. This bridge made things worse. I would be better off having no bridge. Now, this is where the fun is, because it ties to the flow networks I was actually telling you about a little bit earlier. It turns out that this average of the mean first passage time, the all-to-all mean first passage time, can be written as a tau g, which we call the total transit time of all links, which is basically just I take all the edges and I add up the weight of each of those edges and the length to the power 2 beta. There is no explicit topology here. If I add a link, this makes this tau g worse. And then there is this in blue, which is basically the effective resistance of the graph. If this was a flow graph, honest to goodness flow graph, and I pushed flow here, and I wanted to take it out here, the effective resistance of this condition would be the pressure drop or the voltage drop over the current. The effective resistance of all the thing is the all-to-all pairs. So basically this tells me the topology and some stuff about the conductances, the distribution of conductances. It tells me how easy, if I don't know my coming in and coming out, how easy it is for flow to happen. Right? So this ties to an actual flow problem. It basically quantifies, measures the numbers of parallel paths, this effective resistance. Okay, the problem here, the intuition of what I'm going to tell you, and you can fall asleep immediately after this, because that's all you need to understand, is that the shortcut can reduce the mean first passage time of some pairs. Here the color is the mean first passage times. If, let's say, I lost my keys here, right? It's easy to find this node, easy, but it makes it worse for other nodes. And in fact, what happens is that this TG in the augmented graph, if I add this, the total transit time increases here. This becomes better, but it's the competition of these two terms that dictate what's happening. Now, the ones of you that dabble in graph theory, let's say, might have seen this result, which is the Braess paradox. And this basically tells us that it's possible in some nonlinear networks, the addition of extra links to deteriorate the system functionality. This is qualitatively similar, but the physics that brings it is different. It has to do mostly with game theory. But it has been found to be true for real-life situations like New York streets. So if you close the traffic on certain streets, if you remove those streets, that improves traffic. And it's a little bit qualitatively similar in our case. And it goes against the results that people were considering about non-embedded graphs, like small world. In our case, spatial embedding and considering the propagation speed makes this link, in some cases, worse. Now, what are those cases, right? It really has to do with this beta. If beta equals 0, I go to this result, right? And small betas, if I am super diffusive, if I can go faster, progressively faster as the links become longer, it really pays to have many loops. If I am diffusive and above, I should not put links, because I get trapped into links that take a lot of time. I waste my time crossing those big, long shortcuts. And in fact, you can show there is kind of an abrupt transition. I don't know if it's a phase transition. We haven't looked at that. But it's quite interesting. In many quantities here, we look at clustering coefficient, which is the triangles. This is as a function of beta, going from superdiffusion to subdiffusion. Clustering coefficient, effective resistance, you see it increases and then it becomes flat. Weighted topological shortest path. So if something happens close to beta 1, not exactly 1, we'll get back to that. Now, if I keep increasing the size of the system, we see we asymptotically go to 1. So it looks like there is a, it looks like this beta, the transition beta is actually honest to goodness diffusion. And I can do 2 dimensions. It's the same story exactly. Here, what I'm plotting is the average length of the links that remain. And it's actually something interesting that happens. The links, long links get killed in this optimization problem. And actually, the standard deviation of the link length becomes tighter and tighter. I went from this with long range to this, a lattice. The lattice was rediscovered, basically. It's a lattice that spans space, right? And I don't want to go too much. I don't want to go over time. So long story short, 3 dimensions, same story. In fact, it's interesting. Those exponents, transition exponents, which we found numerically, you can predict something very close to them from basically paper and pencil, from this competition. Just look at scaling and that competition. So this is small. We can, if somebody asks me, I'm showing this slide so that somebody can ask me, and I can walk you through this calculation, but it's 4:50, and I don't want to tire you, and I want to finish, and then we can go back to it. So this is, now why we got so excited about this problem. Like in the first problem that I told you, that we're trying to find principles, quote, universal principles for the design of circulatory systems, and maybe how does the signal that your pump in sending the body affects your topology, right? How is that coupling happening, and what does it mean for what the network topology looks like, right? For all types of pumps. Here, we're thinking about maybe communication as a flow problem. And maybe this is, again, this is theory dreams. Maybe this is a platform we can use to unify what's happening at, in situations where long-range links are preferred. If I take a plane to go from, let's say, Philadelphia to Dallas, and from Dallas to Austin, if such a flight exists, it's approximately the same flight, right? The beta is not really subdiffusive in that case. It's on the contrary, right? And we have emerging topologies like this. And then we have subdiffusive stuff. Long-range links are trimmed, right? So maybe there is some way of thinking like this. Now, going back to the particular 2 tales that I told you, and this is my summary. In the first story that I told you, we talked about development with a beating heart, and I told you how periodic forcings stabilize loops, like these dynamics and this time, and how it comes in with this dynamic signaling affects what you look like in the end. Basically, the short time scale due to periodic forcings can determine the final network topology. And another thing which is very important is the geometrically embedded networks. On this project, I returned to geometrically embedded networks, and now I told you how the length and time scaling can determine, the scaling of length to time can determine the final network topology. So again, it's time in these search problems. So with that, I have to say that I started in September. I have a part-time position at the Flatiron Institute, and this is past the deadline, but we're recruiting postdocs, and people can send me applications, and or I think the platform is closed, but people can still contact me if they are interested in working in this kind of problems related to computational biology. So with that, this is my one of the pictures of my group. What you saw in the first part of the problem was primarily work of Purba Chatterjee, which you see here, and a former postdoc, Son Pancher. And what you saw in the second part of the talk with the random walks is work by my graduate student, Giorgos Gounaris. And yeah, thank you very much for your attention.
Why don't you start with one?
Is there any relation between the diameter of the capillaries and the
I don't know. I think so. I don't know. I don't know the exact scaling. I'm sure somebody has looked at it, and in fact, if you want that answer, we have a data set that we're working on something else, but we could produce that in a heartbeat. I mean, it would be faster to produce that in a heartbeat than look it up in a paper. I think there is. Possibly at that level, it's very small. The amplitude of the wave is very, very small, but it is possible. It's a good question for many reasons, though, that also have to do with the flow there is basically red blood cells squeezing past each other, so it's not really an easy fluid to think about, but it's a very good question.
your model with the electricity equation?
Yes.
You had a linear model like a non-slope.
Mm-hmm.
So I assume all of that is low rate of number.
Correct.
Change something in the equations of your vasculature.
Another very good question. Thankfully, for our vasculature, you don't have to worry about turbulence for the most part. So we ignore turbulence. So it's always low Reynolds, but there are other complexities. I'm not saying it's a simple fluid. It's a complicated fluid, but thankfully we don't have to worry about turbulence, but there are other complications. In the second part of the talk.
Yeah.
Yes, this was such a good question. It was almost planted. So we look into not just yet that, but something very close, having allowing links of different beta. And also, we have, on a different context, there is absolutely a way to allow directivity, and in fact, we will do it. We're doing it in the context of energy landscapes. Because the minima, there's a problem there, as you see. The minima are on different heights, and the rate of going from the high to the low is different than going from the low to the high. So that's a necessary ingredient for that model. But that one I don't have results to show you yet, but I can show you about highways, and it is very interesting because it reveals. It's really cool. It looks like there is a length scale that is emerging depending on how that beta is. So if you put that highway, that different link, that's what you're asking. If you have a different link, it looks like in its neighborhood, you develop different behaviors. So that kind of triggers changes in the topology of the network, both locally and globally, that are really bizarre and we don't understand. But I think it reveals a length scale that I don't understand, basically. Anyhow, I don't know. But it's a very good question. Yes. Spot on. Again, another planted question. We have done this different contexts without pulsatility. We've done this for rigid pipes, and it plays a huge role for the stability. So now one ingredient at a time. So we've done the stochasticity. We understand, not only us, stochasticity other people have done with very interesting results. And now we said, okay, temporarily, we're going to forget about stochasticity, and we're going to look the effect of this pulsatility, which is not stochastic. So it's very interesting. At some point, when we want to do more, when we understand both effects, it might be worth putting them together. But it's very cool. In fact, for microvasculature, it's most likely that the stabilization of loops is that stochasticity. And the paper is not only by me, by others as well, that talk about that stochasticity. Ignore that. In fact, not only forget about the blood, or the pipes also, the vessels can be viscoelastic. We do our simple models, which are not viscoelastic at all. And then as next to them, we use models in the literature which up to now don't include viscoelasticity in the fluid, and they claim to this level it doesn't matter. I don't know, to be honest. So I'm worried about all of that, but one step at a time. Okay, so this is another hard question. So first of all, I'll go back and ask another question. What I don't like about thinking there are a lot of people that do optimization in biology, and a lot of it is stories because you don't really know the objective function. That's a big problem. You can try different objective functions, and you can say within this subset of objective functions, the objective function whose optimum is similar to nature is blah. That you can do. The complexity of the problem really depends on exactly what the cost function is. And the problems that I was showing you are non-convex.